Hello, my name is Tessa Kim, and I'm a master's student at CAIST. On behalf of my co-authors, Nitesh, Jeongyeon, Juho, and Ray, I'm happy to present our paper, Supporting Collaborative Sequencing of Small Groups Through Visual Awareness. Collaborative sequencing, or CoSeq, is a type of task in which the members of a group collaboratively construct a sequence by selecting items from a set of possible alternatives and arranging these items into a particular order. People commonly engage in this type of task in both casual and formal contexts. A casual context, for example, is a group of friends planning a trip to Portland and deciding which attractions and restaurants they want to visit and the order in which to visit this. An example of a more formal context can be a group of instructors deciding on the topics to cover for their course and in what order each topic should be taught. In this situation, the group members can be collectively responsible for and affected by the final sequence, and thus building a consensus is essential to achieve high satisfaction regarding the result and intergroup relationships. However, reaching a decision based on all of the group members' consensus can be challenging. Members must expend significant time and communication effort to express their opinions and gain awareness of their other members' preferences. Further, other factors such as individual biases and unequal participation can prevent groups from reaching an effective consensus. Despite the ubiquity of CoSeq tasks and the challenges in consensus building, there is a lack of understanding about these processes, and no systems have been designed to effectively support them. In our work, we aim to determine a design that effectively facilitates consensus building in CoSeq. To this aim, we refer to prior work that demonstrated the benefits of visual awareness for decision-making in diverse collaborative tasks, such as crime analysis and information seeking. Here, visual awareness refers to visual support that allows users to gain and maintain awareness of task and group-related factors. We conducted a formative study where we compared 4 notable prototypes that were designed based on prior work. These prototypes all aimed to help users compare and evaluate sequence-related preferences in a group. The prototypes were A. A list of nodes and edges with visual clues. B. A merge graph that merges sequences into one representation. C. Visualization of edit distance operations. And finally, an adjacency matrix that provides an overview of edges. Participants used these prototypes to compare the travel itineraries of 3 fictional travelers, and then constructed a final itinerary that will maximize the satisfaction of these fictional travelers. By listening from participants what aspects they found useful from each prototype, we derived 3 design requirements for a visual awareness technique. The first requirement is to allow users to learn about selection agreements at a glance. With selection agreements clear, the technique must support users to explore ordering differences when they desire to. Finally, the technique must guide users to actions that can reduce differences within their groups. We instantiated these design requirements in a collaborative travel itinerary planning system, Twine. In Twine, group members are first sent to individual screens, where they first build their personal preferred sequence or travel plan. Then, the group members proceed to a collaborative screen, in which they can see their other members' sequences, compare the sequences, and discuss to reach a consensus on the final sequence. In the individual screen, the user can look at points of interest available and add them to their sequence if they appeal to them. To facilitate recall, each point of interest is represented with a unique icon. The user can also move selected POIs or nodes to change their order. A map is also provided which allows the user to see the geographical positions of the POIs they added to their sequence. After the user and their group members complete the individual planning, they progress to the collaborative screen. In this screen, group members can look at their other members' sequences, with each member being represented in a different color. This screen also provides the visual awareness technique with which the user can gain a deeper understanding of their members' preferences. The technique consists of 3 components. First, our tool provides color coding of shared nodes. For each node in the user sequence, color tabs show which group members also added that node to their own sequence. For example, the group member represented in green also selected International Rose Garden and Hoyt Arboretum. Second, our technique provides ordering details in hover. When the user hovers over one of their nodes, that same node is highlighted in the group member sequences, if they also selected a node. This allows the user to compare the relative positions of that node in their group member sequences. Additionally, details are provided next to the hovered on node to help the user compare what nodes their group members place adjacent to it and what action the user should take to match their group members. For example, as shown, the user has Sangari Pearl restaurant after Cafe Mingo, but to match the group member represented in black, they should add the note with the triangle icon after Cafe Mingo. Third, the technique allows users to see which notes that they didn't select were selected by their group members, and also displays colored tabs to show which group member selected each. The user can easily add these notes to their sequences by clicking on the plus button. By using the visual awareness technique, the user can compare their preferences with those of their group members. And based on this knowledge, they can then discuss with their group members through the chat. The user and their group members can reach a consensus through the discussion and by modifying their own individual sequences to match each other. To understand the effect of the visual awareness technique on the effectiveness and efficiency of the consensus building process in CoSeq tasks, we conducted a within-subject study with 15 groups of 3 friends. Each group performed the same task twice, to construct and reach a consensus on a travel itinerary. This was done once with Twine and once with a control version that did not provide visual awareness support. Regarding efficiency, participants perceived the consensus building process to be significantly more efficient and cognitive workload to be lower with the visual awareness technique. Visual awareness allowed participants to externalize their cognition, as they could easily see agreements and disagreements in opinion and did not have to dedicate significant mental effort to remember this. We also classified the messages sent by participants, and this revealed that visual awareness reduced the amount of messages that participants used to express their own opinions and those used to inquire about others' opinions. Regarding effectiveness, there was a significant increase in participants' perceived group satisfaction during the consensus building process, and this appeared to be due to 2 main reasons. First, visual awareness helped groups notice and carefully discuss the preferences of each group member. Second, the technique highlighted where participants' preferences differed to those of their group members, which encouraged them to match the group members' preferences. While visual awareness appeared to increase group satisfaction, individual satisfaction of participants did not increase significantly. As revealed by participants' comments, this could have been due to the technique being a double-edged sword, encouraging the user to be more thoughtful of others' preferences, but also pressuring them to conform with the majority opinion. Based on the study findings, we distilled 5 main factors of CoSeq tasks, and for each, proposed design implications for future CoSeq support systems. Group size. Despite our focus on a CoSeq task that involved small groups, we still observed that the chat discussions could be disorganized. This would be exacerbated with even larger groups. To handle this, future systems could organize the discussions by anchoring them on the nodes and edges of the sequences. Group hierarchy. Our investigation focused on groups with relatively flat hierarchies. For groups with status differences, systems could be designed to allow all members to participate in the individual sequencing stage and allow those in leading positions to compare all these sequences to reach a final consensus. Sequence length. In tasks with shorter sequences, visual awareness can be more detrimental than beneficial, as it takes focus away from the discussion. With longer sequences, visual awareness should operate on simplifications or summaries of sequences to reduce complexity. Number of alternative items. In our study, identifying new alternatives was a major bottleneck in CoSeq tasks. Future systems could use NLP techniques to analyze the group's discussions and recommend alternatives. Also, if there are too many potential alternatives, it can be more beneficial to scaffold the process so groups consider selection and ordering of items separately. Opinion aspects. In our work, we focus on a CoSeq task where subjective preferences guided the decision-making. In other CoSeq domains, such as managing software teams' workflows or scheduling admission to intensive care units, expertise and knowledge may be more crucial. Future systems could explore how to visualize these additional factors in relation to the sequences. We hope that our findings and our visual awareness technique can guide and inspire the design of future applications to support a wide variety of CoSeq tasks.